Welcome to the lecture series on nonlinear programming. We have already seen what convex functions are, and we have seen some of the important properties of convex functions. Now, we will see some more properties of convex functions. So, epigraph we have already defined. What epigraph is? Epigraph is nothing but epigraph of a function f is nothing but all those x alpha such that x belongs to S, alpha is any real number and fx is less than equals to alpha. This is what epigraph means. Epigraph of function f is nothing but all those x alpha such that x belongs to a set S, alpha belongs to R and fx less than equals to alpha, and it is nothing but a subset of Rn plus 1 that we have already seen, because this x belongs to Rn and alpha belongs to R. So, this is nothing but this triplet will belongs to, this tuple will belongs to Rn plus 1. Now, to show now next theorem states that if S be a convex subset of Rn and f is a function from S to R, then f is a convex function on S if and only if its epigraph EF is a convex set. So, this is the next theorem the result, that f is a convex function on S if and only if its epigraph is a convex set. Now, how to prove this? Let us see. Okay. So, f is a convex function on S if and only if its epigraph is a convex set. So, this is to show. Now, how to show this? So, first we will take that f is a convex function, and then we will try to show that its epigraph is a convex set, and then we will take that its epigraph is a convex set and try to show that its function is a convex function. Now, the first part is, let f be a convex function. Okay, on S. Now, since f is a convex function, this means f of lambda x1 plus 1 minus lambda x2 will be less than equals to lambda fx1 plus 1 minus lambda x2 fx2 for all x1 x2 in S and lambda between 0 and 1. Okay. This is by the definition of the convex function, that f is a convex function if f of lambda x1 plus 1 minus lambda x2 is less than equals to lambda fx1 plus 1 minus lambda fx2, and this must hold for all x1 x2 in S and lambda between 0 and 1. Now, what we have to show? We have to show that if f is a convex function, then its epigraph is a convex set. To prove this, take two arbitrary points in the epigraph, in the set that is epigraph, and try to show that the convex linear combination of those 2 points is in S. Okay. So, let x1 alpha 1 and x2 alpha 2 are in epigraph of the function f, because the points which are in epigraph are like this, x comma alpha types. So, it will be x1 alpha 1 and x2 alpha 2. Let us suppose it belongs to this epigraph. So, it means that fx1 will be less than equals to alpha 1 and fx2 will be less than equals to alpha 2 by the definition of epigraph. Okay. Now, take the convex linear combination of these 2 points. Okay. The convex linear combination will be nothing but lambda or times of first point and 1 minus lambda times of second point, and say it is some x comma alpha for lambda between 0 and 1. Okay. So, let us suppose the convex linear combination we represent this by x comma alpha. So, what will be x? X will be lambda x1 plus 1 minus lambda x2 And what will be alpha? Alpha will be lambda alpha 1 plus 1 minus lambda alpha 2. Now, to show that it is a convex set, we have to simply show that x comma alpha belongs to epigraph, that is EF. Okay. That means we have to show that fx is less than or equals to alpha. So, take f of x and try to show that it is less than or equals to alpha. So, what will be fx? Fx will be nothing but f of lambda x1 plus 1 minus lambda x2, and by the definition of convex function it is less than or equals to lambda fx1 plus 1 minus lambda fx2, and fx1 is less than or equals to alpha 1 and fx2 is less than or equals to alpha 2, because these points are in epigraph of f. So, this implies that is less than or equals to lambda alpha 1 plus 1 minus lambda alpha 2, because this lambda and 1 minus lambda are non-negative values, they are lying between 0 and 1. Okay. So, and this is nothing but alpha, this is nothing but alpha. So, we have shown that f of x is less than or equal to alpha. So, this means if f of x is less than or equal to alpha, this means x comma alpha will belong to the epigraph. So, this implies x comma alpha will belongs to epigraph of the function f, and that means epigraph is a convex set. Okay. So, in this way we can say that if function is a convex function, that then its epigraph is a convex set. Now, we will try to prove the converse part. We will take that a epigraph is a convex set and we will try to obtain that the function f is a convex function. Now, let us see. So, now for converse part, let epigraph of the function f be a convex set. Okay. Now, we have to show that function is a convex function. So, if its epigraph is a convex function, take two arbitrary points. Now, x1 comma fx1 and x2 comma fx2 will definitely belongs to epigraph of f. This is because it is alpha 1. Now, fx1 is less than or equal to alpha. This is obviously true because equality holds. Okay. If it is alpha, fx1 is less than or equals to alpha, alpha is fx1, fx2 is less than or equals to fx2, it is obviously hold. So, these point definitely belongs to epigraph of the function f. Now, it is given to us that the epigraph is a convex set. So, this means, this implies lambda times the first point and 1 minus lambda times the second point must belongs to the epigraph for lambda between 0 and 1. Okay. So, this implies lambda x 1 plus 1 minus lambda x 2 and lambda fx 1 plus 1 minus lambda fx 2 must belongs to the epigraph of the function f. Okay. Now, it belongs to the epigraph means what? If x comma alpha belongs to the epigraph, this means fx is less than or equals to alpha. So, this is some x and this is alpha. Okay. So, this x comma alpha belongs to the epigraph means fx is less than or equals to alpha. So, fx is f of x is this quantity, this term is less than or equals to alpha, and alpha is this quantity lambda fx1 plus 1 minus lambda fx2, and this implies that f is convex, is the convex function on S. Because x1 and x2 are any arbitrary points, this means this result hold for any x1 and x2, and hence function is a convex function on S. So, in this way we can say that if epigraph of function is a convex set, then also we can say that a function is a convex function. Okay. So, if we have to show that a function is a convex function, either we use the definition of the convex function, which is f of lambda x1 plus 1 minus lambda x2 less than equals to lambda fx1 plus 1 minus lambda fx2, or we can also find this epigraph and try to show that epigraph of the function f is a convex set. Okay. Now, similarly, using hypograph, hypograph is a hypograph of function f is nothing but all those x alpha such as x belongs to S, alpha belongs to R, f x greater than equals to alpha. So, this is hypograph function f. So, if S is a convex set and f is a function from S to R, then f is a concave function on S if and only if its hypograph is a convex set. So, the proof of this can also be obtained on the same lines, on the lines of the proof which we did earlier. Okay. So, in order to prove that a function is a concave function, find its hypograph and try to show that a hypograph of the function f is a convex set. Okay. Now, we have a result now. Let fi be a family of functions which are convex and bounded from above on a convex set S subset of Rn. Then the function which is given by a supremum of fi is also a convex function. So, let us try to prove this. So, for example, suppose you are taking maximum of x and x square. Okay. Now, both functions are convex. X is a linear function, it is convex if function is from R to R, x belongs to R. X square is also a convex function, that we have also seen that x square is a convex function, and maximum of two convex functions also convex. Okay, that we can easily show, we can easily see graphically. See x y equal to x is this line, okay, and y equal to x square is this. This is the intersection point. Okay. Now, what is the supremum of this function? Supremum of this function is if we take function from say from 0 to 2. So, 0 to 2 it is nothing but from here to here this is the maximum value when it is 1, okay, and from 1 to 2 this is the maximum value, this curve. So, this shaded line and this is the maximum or the function from 0 to 2, say 2 is here, okay, say 2 is somewhere here. So, the maximum of x and x square is this function. Now, if we take the epigraph of this function, so epigraph of this function is nothing but this set, and which is convex, and since it is convex, so we can say by the theorem that the concerned function, if it is a function f, then this function is a convex function. So, this is this theorem that the supremum of fi is also a convex function. The proof is very simple, can be obtained. Let us try to obtain the proof. Now, fi are convex functions on S for all I. So, this implies, because we know a theorem that if functions are convex then its epigraph is a convex set. So, this implies E of fi are convex set for all I, and since it is a convex set, so this means intersection is also a convex set. Because intersection of any number of convex set is also convex. Okay. Now, let us see the intersection of EFI, what this represent. This is nothing but all those x alpha such that x belongs to S, alpha belongs to R, and fi x is less than equals to alpha for all I is a convex set. Intersection of E of fi is a convex set. What does intersection represent? Intersection of E fi represent all those x alpha such x belongs to S, alpha belongs to R, and fi x less than equals to alpha for all I, because it is an intersection, that means for all I is a convex set. Now, if it is true for all I, this means it will be equals to, it will be equal to supremum of I also. Supremum I less than or equals to alpha is also a convex set. Okay. And this is nothing but is equals to all those x alpha such that x belongs to S, alpha belongs to R, and supremum of Fi is nothing but Fx. So, it is Fx less than or equals to alpha is a convex set. So, this means epigraph of F, where F is nothing but supremum of Fi, is a convex set. And since epigraph of F is a convex set, this means F is a convex function. Convex function on S. Okay. Because we know that if epigraph of a function is a convex set, this means the function is a convex function, and since epigraph of F is a convex set, so this implies the concerned function, the corresponding function is a convex function. And what is the corresponding function? It is nothing but supremum of Fi. So, hence we can say that if we have a collection of a convex functions, the supremum of the convex functions is also convex. Okay. Now let us define differentiable convex functions. If let f be a function from S to R be differentiable at x bar belongs to S, where S is an open subset of Rn, then for x plus x bar belongs to S, f of x plus x bar will be equal to f of x bar plus x transpose gradient of f x bar plus alpha is a function of x bar and x and norm of x, where this term will tend to 0 as x tending to 0. So, this is how we define a function is once differentiable at x bar belongs to S. Okay. What is gradient of f x bar? Gradient of f x bar is a vector basically. So, gradient of f at x bar is nothing but del f upon del x1, del f upon del x2 and del f upon del x. So, this is gradient of f x bar. Okay. Now, if a function is twice differentiable at x bar, then f of x plus x bar is equals to f x bar plus x transpose gradient of f x bar plus half of this term plus beta x bar x norm of x square, where this term tend to 0 as x tending to 0. So, this is how we can define the function f if function is once or twice differentiable at x bar. Okay. Now, what is gradient square of f x bar? Let us define this thing also. Gradient square of f x bar is nothing but a matrix, and we call it Hessian matrix. We call it Hessian matrix of f at x bar. And what it is? It is nothing but del square f upon del x1 square, del square f upon del x1 del x2 and so on, del square f upon del x1 del xn, then del square f upon del x2 del x1, del square f upon del x2 square and so on, del square f upon del x2 del xn, and it is del square f upon del xn del x1, del square f upon del xn del x2 and so on, del square f upon del xn square. So, this is how we can define n cross n symmetric matrix, which we call as Hessian matrix of f at x bar. Okay. This is gradient square of f at x bar. Now, we have our next result for a convex function, which is if f is a function from S to R, which is differentiable function on a open convex subset S of Rn, then the function f is a convex function if and only if f of x1 minus f x2 is greater than equals to x1 minus x2 transpose gradient of f x2, and this should hold for all x1 x2 belongs to S. So, now let us try to prove this result. So, what this result is basically, this is f x1 minus f x2 is greater than equals to x1 minus x2 transpose gradient of f x2, and this should hold for all x1 x2 belongs to S. And what we have to show, that f is a convex function on S if and only if this happens. Okay. So, first let us assume that f is a convex function, and we will try to show that this result hold. Okay. So, first let f be a convex function. On S. Okay. Let f be a convex function on S. So, convex function means f of lambda x1 plus 1 minus lambda x2 must be less than equals to lambda f x1 plus 1 minus lambda f x2 for all x1 x2 in S and lambda between 0 and 1. Okay. Now, what is f of lambda x1 plus 1 minus lambda x2? It is nothing but it can be written as f of lambda x1 minus x2 plus x2. You can take this lambda common from these two terms, it is lambda of x1 minus x2 plus x2. Now, it is given to us that function is differentiable on an open convex set S of Rn. This means differentiable for all points in S. Okay. So, if it is differentiable, this means the first result holds. Okay. So, let us try to use this result. So, here suppose this is x, this quantity is x and this is x bar. Okay. So, you use this result, it is x bar. So, it is equal to f of x bar plus x transpose gradient of f x2 plus alpha times x bar and x and norm of lambda x1 minus x2. Okay. This is simply by this result. Okay. And where this limit tending to 0, where as limit of alpha lambda x1 minus x2 comma x2 will be equal to 0 as lambda tending to 0 here. So, f of x plus x bar is equals to f of x bar plus x transpose f x gradient of f x bar plus alpha function of x bar and x and norm of x. Okay. So, now this is equals to, now this quantity from this expression is greater than, is less than or equals to lambda f x1 plus 1 minus lambda f x2. Okay. From this expression, this quantity is less than equal to, means this is equal to this, means this expression is less than equal to this quantity. So, what we obtain from here? This implies f of x2 plus lambda times x1 minus x2 transpose, because lambda is a scalar we can take it out, and it is gradient of f x2 plus alpha function of lambda x1 minus x2 comma x2 Now lambda can take out because it is between 0 and 1, and norm of x1 minus x2, which is less than or equals to lambda fx1 plus fx2 minus lambda fx2. You multiply fx2 here. Now this fx2 and fx2 cancels out from both the expressions. You divide by lambda throughout. So what we obtain? We obtain that x1 minus x2 whole transpose gradient of fx2 plus alpha lambda into x1 minus x2 comma x2 norm of x1 minus x2 is less than or equals to fx1 minus fx2. Okay. Now take lambda tend to 0 both the sides. If you take lambda tend to 0 both the sides, so this term will tend to 0. If so, taking lambda tend to 0 implies x1 minus x2 whole transpose gradient of fx2 is less than or equals to fx1 minus fx2. Okay. So we have proved the first part. So we have taken that f is a convex function, and we have obtained that f of x1 minus fx2 is greater than or equals to x1 minus x2 transpose gradient fx2. Okay. Now we will try to show the converse part. Okay. So in the converse part, we will suppose that this condition hold and try to obtain that the function is a convex function. So, let x equals to lambda fx x1 plus 1 minus lambda x2, where lambda between 0 and 1. Now, this inequality hold for every x1 and x2, and x is a convex subset of Rn. Okay. So, this will hold for x1 and x also. So, if we apply for x1 and x, so this will be greater than or equals to x1 minus x transpose gradient of fx. Okay. Because we have supposed that this condition hold. This condition hold means this inequality hold for all x1 x2 in S, and we have to show that the corresponding function f is a convex function. Okay. So we have so this result will hold for x1 and x also. So we have applied this result for x1 and x. So we obtain this thing. So what it is equal to? It is equals to x1 minus x. x1 minus x will be nothing but 1 minus lambda times x1 minus x2 transpose gradient of fx. So suppose it is the first expression. Now the same result will also hold for x2 and x. Okay, because it is holding for all x1 x2 in S, and this is in S because S is a convex set. Okay. So fx2 minus fx again will be greater than or equals to x2 minus x whole transpose gradient of fx. Now what is x2 minus x? When you compute x2 minus x, so it will be nothing but x2 minus x will be nothing but minus lambda times x1 minus x2 whole transpose gradient of fx. Okay. Now we have to obtain that, we have to derive that function is a convex function. That means f of lambda x1 plus 1 minus lambda x2 is less than or equals to lambda fx1 plus 1 minus lambda fx2. So we have to obtain that result. So you multiply this with lambda and this with 1 minus lambda. Okay. Multiply 1 with lambda and 2 with 1 minus lambda and add them. So what we obtain? We get lambda of fx1 minus lambda fx from this side plus 1 minus lambda fx2 minus 1 minus lambda fx is greater than or equals to Now, when you multiply this with lambda and this with lambda and this with 1 minus lambda and add them, so both things will cancel out. So, we will get 0 on the right hand side. Okay. So, what we obtain from here? This implies lambda f x 1 plus 1 minus lambda f x 2 will be greater than or equals to lambda f x and lambda f x will cancel out. So, this will be greater than or equals to f x, and x is nothing but the convex linear combination of x 1 and x 2. So, which is nothing but is equals to f of, you substitute the value of x is this quantity. So, it is lambda x 1 plus 1 minus lambda x 2. So, hence we have obtained that f of lambda x 1 plus 1 lambda x 2 is less than or equals to lambda f x 1 plus 1 minus lambda f x 2. This implies f is a convex function. Okay. So, we can easily see that if f is a convex function, then f of x 1 minus f of x 2 will be greater than or equals to x 1 minus x 2 transpose gradient of f x 2. Now, what this expression geometrically indicates, let us see. Okay. Let us see what this expression geometrically indicates. So, you draw the function f, take a point x 2, suppose this is x 2, draw a tangent at this point. Tangent will be nothing but this straight line. Okay. Take another point, say x 1 here. So, what this will be? This length. So, from here to here it is x 2, from here to here it is x 1. So, it will be nothing but x 1 minus x 2, this quantity. Okay. So, what will be the equation of this line? Now, at the point x 2 comma f x 2, the equation of the line will be nothing but y minus f x 2 is equals to m is the slope of the line, slope is f dash x 2 and x minus x 2. Okay. Now, we want to find out this point. We want to find out this point. So, this point will be nothing but to substitute x as x 1, x as x 1. So, what we obtain? So, y will be nothing but f x 2 plus x 1 minus x 2 f dash x 2. So, this if you are taking as this as x 1 comma y. So, this y is nothing but this expression, and you can easily see that this point is nothing but x 1 comma f x 1. So, x 1 is f x 1 is this this height f x 1 and this is f y, this is y. Okay. So, f x 1 is greater than or equals to y. So, f x 1 is greater than or equals to y means this expression. Gradient, or for the first case it is derivative. This expression means this result. So, that means that if you draw a tangent at any point on the convex function, that tangent always lies below the curve. If you take, because this length is always less than this length. So, that means if you have a convex function and you draw a tangent at any point on the convex function, the tangent always lies below the curve. Okay. So, this is geometrical interpretation of this inequality. So, we can prove some functions to be convex using this expression also. How? So, let us see one example. Suppose you have to show that function x square, where x belongs to R, is a convex function. So, we have already seen that we can also show this as a convex function simply by applying the definition of the convex function, but we can also show this to be convex using this result. Now, let us see what is fx1 minus fx2 minus x1 minus x2 transpose derivative of x2, because it is in R, okay. And we have to show that this quantity is greater than or equal to 0. Then we can say by this theorem that function is a convex function. So, what this expression is for this function? It is x1 square minus x2 square minus x1 minus x2. What is the derivative of this function at x2? It is 2x2. So, this is nothing but x1 square and this is plus x2 square minus 2x1 x2, which is nothing but x1 minus x2 whole square, and which is greater than or equal to 0 always for all x1 x2. So, this implies function is a convex function, because this inequality must be greater than or equal to 0, and that we have shown that for this function x square this inequality is greater than or equal to 0. Hence, we can say that the given function x square is a convex function. So, sometimes to prove that a function is a convex function, we can also use this definition. Okay. So, we will see some more properties of convex function in the next class. So, thank you.